Hello, everybody. Welcome to the AI Club. So I'm Shruitika. I am having around 13 plus years of experience in various domains and technologies. Have worked with companies like Infi, Accenture, Mindtree, and now I am a freelance trainer on data science. So in this video, we are going to talk about decision models theory. And then in another video, we will also do a code walkthrough of a Python hands-on exercise. So let us give a quick start to our session now. So first of all, what is a decision tree model? So in layman's terms, if we say, it is a most simplistic model, which even a layman with non-mathematics background can understand. Okay, so earlier we have seen that linear regression, and then if you go further in deep learning, there is lot of complex mathematics involved. But when it comes to decision tree, so we will be able to explain this model even to a person with non mathematics background. So it is a very simplistic model, and it is mainly used for classification problems, but it can be used for regression problems also. And it is a supervised learning model, which means that we are having the target variable with us, and during training we will be having the target variable, and uh, on this data set, which has both dependent features as well as the independent features, we will be training our model. So it is a supervised model where both target and independent variables are present. So here you are able to see some graphs with scatter plots. Okay, so you can see in the left scatter plot, there are some points, some are blue points and some are green points. So if we want to segregate these two kinds of points, so we can consider them as two classes of a classification problem. Some data set is there, which is having the uh, target variable with two classes. Okay, so the class 1 can be represented by blue points and the class 2 can be represented by green points. And in this way, depending on the various features of x and y, we are getting a scatter plot. And our aim is to have a line of separation, a simple line of separation between the blue and the green dots. So in the right graph, if you can see, okay, we have created a line where x is equal to 2. Okay, and on this line, we can see a clear separation between the blue dots and the green dots. So we can say that this x is equal to 2, this can be our model, and we can use this model to segregate both the classes. So this is a kind of perfect split. If you can see that there are no errors. Okay, on the right side there are only green balls, and on the left side of the line, the model, there are only blue balls. So we can say that it is a perfect split. So now, what is a decision tree model and why is it needed? So now, if you see this PPT, now let me first go through the definition of decision tree that is written, and then we will analyze what we are doing using the X and Y values. Okay, so decision trees are a non-parametric supervised learning method used for both classification and regression tasks. Fine. So the decision trees may not be having parameters like we have seen in linear regression and other kind of algorithms. Lot of parameters or hyperparameters will be involved. So that many parameters won't be involved in the decision tree. And it can be used for both classification as well as regression task, and it is a supervised learning method, as we have discussed these things earlier also. Then the decision rules are generally in the form of if then else statements. The deeper the tree, the more complex the rules and fitter the model. Okay, so now you can see a data set is there where x and y, these are the features or the independent variables, and x and y, this column contains the target variable, which is depending on x as well as y. So if you can observe, it is an AND gate which we have applied on x and y. So if the value of x is 0 and y is 0, then the value of x and y is also 0. Now, if x is 0 and y is 1, then still we are getting an output of 0. X is 1, y is 0, again output is 0, and only when both x and y are 1, then we are getting an output of 1. So this is a normal AND gate that we have applied on both x and y features. So in the right, we have tried creating a decision tree. Okay, so sometimes this kind of thing you would have seen when you would have created some flow charts. Um, just like in initial days of learning programming, you may have created flow charts where you try to depict the algorithm using some kind of what I can say, some kind of diagrams where some decision boxes are involved and some control statements are involved. So you can see somewhat similarity here in the decision tree. Okay, so we have taken the first feature as x. Okay, and we have applied the decision as whether x is greater than 0 or not. Now, if x is greater than 0, you can see that the the branch is going towards the left. Okay, and if x is less than 0, then anyway we are going to get an output of 0, so we have written the output as 0 in red font. Now if x is greater than 0, then we can see that it further gets down to whether y is greater than 0 or not. Means then it depends on the value of y. If x is greater than 0, then it depends on the value of y whether the target is going to be 0 or 1. So in short, I can say that if x is greater than 0, then the target value is equal to the y value. That is what we can see in the tree showing us. And if x is less than 0, then always the target is 0. So a very simple kind of decision tree you can see here in this slide. Moving forward, so here the same thing we have done. Like here we have directly said that if x is greater than 0, then the value of target is equal to the value of y. So here we are further detailing it down. Okay, so if y is greater than 0, then we are making the target as 1, otherwise we are making the target as 0. So here you can see, the if you go to the bottommost part of the tree, some ones and zeros, you can see 1 in green and 0 in red. Okay, so these are called the leaf nodes of the tree. Okay, or the terminals of the tree. Terminals, because now the tree stops growing on these terminals. Okay, so just going through the terminology, a decision tree is a tree like graph with nodes representing the place where we pick an attribute and ask a question. Edges represent the answers to the question, and the leaves represent the actual output or class label. They are used in non-linear decision making with simple linear decision. Okay, so as we further go down, we will get into the terminology in a better way. But as of now, you can see that the edges represent the answers to the questions. As you can see here, if x is greater than 0, then we are saying that uh, it is equal to y. then we are picking the feature as y. So we will further discuss this down in some of our next slides. So, and one important thing to discuss here is the decision trees are used in non-linear decision making with simple linear decision surface. So decision trees will be used when somewhere we have a notion that the independent features are not having a linear relationship with the target variable. Okay, in that case, we will go for decision trees. So now here a similar tree we have tried creating for an XOR gate. So when the value of A and B both is false, the target is false. Okay. And if A is false, B is true, the target is true. In this way, in the very obvious XOR gate, so I don't need to explain this XOR gate here. Now we will see how we have created the decision tree for this kind of gate. Okay, so first of all, we have picked up the feature of A. Okay, if A is false, then we are checking the value of B. So here, if you see, if A is false, then we check B. Okay, if B is false, the target is false. If B is true, the target is true. That is what it is written here. If A is false, we are checking B. If B is false, the answer is false. If B is true, the answer is true. Similarly, if A is true, again coming back to this table, if A is true, then if B is false, then the answer is true. And if B is true, then the answer is false. So if coming back to the tree now, if A is true, we are checking the value of B. If B is false, the answer is true. If B is true, the answer is false. Okay, in this way, you can see that the tree has been created. So any kind of values of A and B, if they are given, traversing through the tree, we will be able to arrive at the results of what we will get for A's or B. So in this slide, here now instead of using some XOR and AND gates, we have tried using some real-time scenario. Okay, a decision tree for the notion play badminton. So here are some independent features like weather, temperature, humidity, and wind. And depending on these climatic conditions, we have to predict whether a match is going to happen or not. Okay, so just going through a few rows of this data set, if weather is sunny, temperature is hot, humidity is high, and the wind is weak, then the match is not going to be played. Okay. Now, if weather is cloudy, temperature is hot, humidity high, wind is weak, then the play is going to happen. That is what play is equal to yes. So in this way, we are able to see some data. Now, what we have done is we want to create a decision tree. So we have picked up the first feature as weather. Okay, now the weather, it is a categorical features and it is having three values: sunny, cloudy, and rainy. Okay, so that is why we have created three branches or three decision trees for weather, um, corresponding to the three values of this feature. Fine. Now if you see, when the weather is cloudy, okay, in the row number 2, the weather is cloudy and the play is yes. Then in the row number 4, again weather is cloudy, play is yes. And the day 9, weather is cloudy and play is yes. So from the data, we can make an inference that whenever the weather is cloudy, always the game is going to happen, irrespective of whether the temperature, humidity, or wind, whatever be the values of the other features, the game is going to happen. So that is why, if you can see in this cloudy branch, okay, we got a leaf node here, the terminal node here, which always says yes. So whenever weather is cloudy, the game is going to happen yes. Now when the weather is sunny, okay, now if we see here in row 1, weather is sunny and the game is going to happen is no. Now coming to row number 3, weather is sunny and the play is going to happen is yes. So it means that the target variable, in addition to this weather feature, it is depending on some other features also. Okay, so that is the reason in this weather equal to sunny branch, now we are checking humidity. Okay, and the combination of weather as sunny, humidity as high, we found that the play will never be played. Okay, that play is no. So that is why we have written no here. And if humidity is normal, it is yes. Play is going to happen is yes. Okay, and in the same way, when the weather is rainy, again we saw that the play is depending on other features, that is the wind. Then we are checking the wind values, and depending on the values of wind as strong or weak, we are arriving at a result that whether the play is going to happen or not. So it is a typical decision tree that is shown in this slide. So now moving further, now, in this slide, we have seen that all the variables are categorical variables. In the next slide, we can see that instead of categorical variables, we can have some of the variables as numeric also. So that is why whether we have kept as sunny, cloudy, rainy, and then for humidity, we can see some numeric values as greater than 75%, less than 75%, and similarly for wind also. So it is just a small variation of the decision tree, a small another kind of decision tree where the features are having both categoric as well as the numeric value or the continuous attributes. So moving further down. Okay. So now we will see what are the root nodes. Earlier I talked about leaves, and so let we will discuss it in further detail that what exactly these things are. So a decision tree is a tree-like graph. You can see the tree like graph, the topmost tree always, it generally, if you normally take a eucalyptus tree or a Christmas tree kind of thing, so at the top there will be a tip, and then it further spreads as we go down. So that is what we can imagine it to be a kind of tree only. Okay, so a decision tree is a tree like graph with nodes representing the place where we pick an attribute and ask a question. Then edges represent the answers to the question, and the leaves represent the actual output or class label. And they are used in non-linear decision making with simple linear decision surface. So what exactly all this text means is, at the topmost tip of this tree, it is called the root node. Okay, the first node is called the root node, and after that you can see some of them will be the decision nodes where the decisions will be taken, and some will be the terminal nodes, the nodes where the tree stops growing. You don't see any child nodes after the terminal node. Okay, so these terminal nodes are also known as the leaves of the decision tree. Fine. So again, here we have given it with the terminology, and here for the terminology we have provided some values, some features, and the values corresponding to those features. Now, what are the advantages of decision trees? Why we use decision trees when we have other algorithms like linear regression is there, and then we have some other things also with us? Then why specifically decision trees? So the first thing is easy to use and understand. So as we have seen, there were some simple if and else statements, and depending on that, we were segregating the data. so it is very easy to use and understand. Then it can handle both categorical and numerical data. That is what we have seen in our previous slides, that some of the features, they were having numerical data and some were having categorical data. Fine. And in decision trees, we don't need to encode the categorical data. It is able to handle the categorical data as it is. So this is also one of the benefits of using decision trees. Then resistant to outliers, hence require little data processing. Resistant to outliers means it can handle outliers. In linear regression, we had seen that if we are having outliers, then our results start varying. Okay, the model, the best fit line, it may also change. The various the coefficients that we got, they may also change. And finally the MSE that we are getting, mean square errors, they also change very highly. The variances change, and which may give us a wrong impression, their impression that our model is not working properly. But in this case, they are resistant to outliers. So if you would have done some of the use cases for linear regression, you would have seen that half of the time or half of the code is only for data visualization and data pre-processing. That is data engineering. Okay, first of all, we have to check various the correlations. That's correlations anyway we can check in decision trees. And then we have to encode the data, the categorical data, and then we have to work with the outliers. So this data processing takes lot of effort when we consider linear regression. But when it comes to decision trees, so the code required for these type of handling is not there. So in one way, the lines of code are reduced, thereby the effort is reduced, and further going down, the maintenance for the project may also reduce. Okay. And then the new features can be easily added in decision trees and can be used to build larger classifiers by using ensemble methods. So later you will come to know that when we have huge amount of data and lot of complexity is involved, and when we see that just one kind of algorithm is not working, then we try to combine multiple algorithms. Okay, which is called ensembling technique. So it can be like XGBoost or random forest. These are different ensembling techniques, where what we do, we create a number of decision trees and we try to join these decision trees, and then depending on various factors, we may be taking the mean of the final result. Or if it is a class, then the highest probability will take the precedence. So in this way, we will try creating ensemble methods, and these decision trees, they are highly used to create those random trees and XGBoost kind of ensemble methods. So what are the disadvantages of decision trees? So disadvantages are, it is prone to overfitting. So just to recollect the idea of overfitting, we have seen in linear regression also that sometimes what happens is when we are training the model. Okay, so sometimes the model tends to learn the data. Okay, so what happens because of this process, it starts giving very good accuracy for the trained data. But when we feed some test data or some unseen data to the model, then it fails badly. Okay, the results, the accuracy that we get, it is very bad. So which is called overfitting, and these decision trees are very much prone to overfitting. It is possible that for training we get very good data, but when it comes to test, the accuracy reduces significantly. Okay, then they require measurement as to how well they are doing. So anyway, the measurements are required. Any algorithm you take, measurements are a must to know how well they are doing, but it needs some typical kind of measurements here, which can be seen later. then need to be careful with parameter tuning, and can create biased learned trees if some classes dominate. Okay, so if it is not a balanced data set and some of the classes they are dominating, then the results that we may get, it may be a result of the biased learned trees. Okay, the trees may get biased and give some results which are not up to the mark. So again, coming back to this badminton playing notion use case. Okay. Now, one of the question, after discussing so many things, that we pick up one of the features, then we segregate the data depending on the various conditions on that feature, and then in this way we keep on picking up the features, segregating the data until we come across some leaf nodes or the terminal nodes. Okay, so this we have discussed till now. Now, one of the major factors that would have come to your mind is, what is the criteria of picking up the features? Okay, what is the criteria that we have picked up weather first, and then going down we have picked up humidity in this case and not wind, and in right we have picked up wind and we have not considered humidity anywhere. So what is the criteria for doing all these things? Okay, so that we will discuss the criteria, we will have to discuss. So just the text that that the slide says is like, given the above four features, how do you decide which feature to split on first? Can you randomly select any feature and split the data set on it? So this is a question that is it okay if randomly we are picking up any feature and at random we keep on doing it? Will we be getting correct accuracy always? And or should there be a selection condition to choose a particular feature ahead of the other three features? So this is a hanging question actually now before us, when we have discussed lot of things like advantages, disadvantages, what are decision trees, why they have to be used. Now the first question, the first hanging question is how to pick up the features for splitting the data. So to understand this thing, first of all, we will have to understand the concept of heterogeneous and homogeneous. So actually this thing is something in high school itself we study the heterogeneous mixture and homogeneous mixture. So it should be well understood, but just to repeat the things, um, on the left side, you can say that we tried splitting the data set, and in both the boxes, there are equal number of plus and minuses. Okay, so it is a kind of heterogeneous data set where we are getting both the kind of classes in equal numbers. Okay, and coming back to the right side, here we tried, see, you can see that in both the right and the left boxes, the parent node, the root node, is having the same number of both the classes plus and minus. Okay, but the way we have segregated the way we have separated the data set in the left, it's such that whatever the result we get, it is it is like there is no more improvement in the segregation. uh, in the parent also equal number of plus and minus, and in the child also equal number of plus and minus. So we are not actually getting anything by splitting in this way in the left side. And in the right side, if you can see, we have segregated in such a way that most of the pluses are in one box and most of the minus are in another box. Definitely there are some variations, but the variations are very like negligible. Okay, so now in this case the prediction for us will be easy, that if some data is there, which after all this if and else statements, if it is finally bringing us to the right box, it means that it is going to be the minus class. And if the data comes to the right class, it means mostly our prediction will go towards the data to be the plus class. Okay, so it is becoming easier for us to predict the class if we are segregating the data in this way, such that most of the classes of one type are in one box and most of the classes of another type are in another class. Okay, so the splitting in the right box is correct, while the splitting in the left box, it is not giving us any information, or we are at the same place even after splitting. Also we are at the 50-50 place, that if we take any plus minus from any of the box, there is a 50% chance that we will get class plus or class minus. Okay, so the thing is, try to split the nodes such that the resulting nodes are as homogeneous as possible. So this is the rule of the thumb that we have to use while creating the decision tree, that try to split the nodes such that the resulting nodes are as homogeneous as possible. So just to stress on the idea of heterogeneous and homogeneous mixture, here you can see that some sand and water mixture, and definitely you can see that you are this the sand and water, they are in equal proportion, you can see there. Okay, and in the sugar and water, this is a homogeneous mixture where water can be seen clearly in the glass. Okay, so some repetition of this concept, but otherwise I think you would have known from this picture itself what exactly we mean by heterogeneous and homogeneous, and why we prefer homogeneous split for a decision tree. Okay, so now moving further, a split that gives you a homogeneous subset is much more desirable than the one that results in 50 to 50 distribution. In the case of two classes, all the data points belong to one class in a completely homogeneous set. Okay, so the first rule of thumb is we need to segregate in such a way that the homogeneous the so that we achieve the maximum homogeneity. Okay, so now here also you can see the bigger circle. Here just 50-50 chance, because there are three red balls and three green balls, so the chance of we picking up red ball is just 50%. It is exactly same as we picking up the green ball, which doesn't make any sense. Okay, and it is a heterogeneous set which is not at all required. After a split, we should get a homogeneous set. While we just see the oval circle, oval shape, there it is a homogeneous thing where we can see classes of only one type in that set. Okay, now pick an attribute and split the data such that the homogeneity increases after every split. Fine, so we have to, if there are some n number of features, so we have to pick up the that feature, and we have to make the decision in such a way that when the decision is applied and when the data is split, we get the maximum homogeneity. And this should apply to each and every split throughout the decision tree. And you stop splitting when the resulting leaves are sufficiently homogeneous. Okay. When we get a actually perfect homogeneous thing is not possible in the real time scenarios, but at least some sufficiently homogeneous, like in linear regression we saw that accuracy, we want some accuracy of 90%, 95%, something like that. So in decision tree also, we need some sufficiently, some acceptable homogeneity. So now how to measure the homogeneity? So these are a few of the measures. One is the entropy. The entropy also in high school science subjects you would have read through it. So entropy is a major measure of disorder or the impurity. So entropy is high when there is a higher degree of disorder or impurity. So if I ask you in the bigger circle where the this thing you can see two circles here, one circle with the equal number of red and green balls and another smaller circles with only violet box. So could you tell me where the entropy is going to be high? So definitely because the disorder is high in the bigger circle, so entropy is going to be high here in the bigger circle, and it is in a more, the smaller is in a more orderly fashion. So the entropy is going to be lower here. Now, after entropy, there is one more thing which is called the information gain. So information gain is a statistical property that measures how well a given attribute separates the training examples according to their target and classification. Okay, so the information gain is a statistical property that measures how well a given attribute separates the training examples according to their target classification. So now if you see here in our left side tree, okay, the split doesn't make any difference. Okay, both are having the equal amount of plus and minus classes. So there is very low information gain or zero information gain in this case. We are not getting any information out of this kind of split. Okay, so that is why the information gain is very slow, very low. And now if we come to the right decision tree, the split we have made is such a way that most of the plus classes are in one box, most of the minus classes are in another box. So this time now the information that we are having, that if this is this box, then definitely plus, it has to be plus class. If this is another box, then it has to be minus class. So the information that we are getting out of this split is much higher as compared to the information that we got from this light uh, left side of the tree. Okay, so this is what it means by the information gain. Now there are some formulas and measures for this thing which we will further see, but physical significance or from the point of view understanding, information gain means only this thing, that by after splitting, if we are able to get um, after splitting, if we are able to separate the training examples according to their target classification, then it is a high information gain. Otherwise, it is going to be a low information gain. Now, we will come to the mathematical concept of entropy and information gain and see what are the formulas for this thing. So, information gain is the reduction in entropy. Just give me 1 minute. Um, there seems to be some problem with the share. Okay, so now it is good. Now, information gain is the reduction in entropy. Okay, so if the entropy is high, that means the disorder is high. That is why the information gain is low. And in if the, when the entropy goes down, so that the data comes in order, so the information gain is high. Okay, so in this way you have to understand, if information gain increases, entropy decreases. If entropy increases, information gain decreases. Okay, maybe you can say they are inversely proportional in some way, you can say. Now, information gain is calculated by comparing the entropy of the data set before and after a transformation. Fine. So what we do is, we take a data set, we find the entropy, we calculate the entropy of that data set depending on some formula. That is the first entropy. Now we split the data depending on some feature and some decision. And then we again calculate the entropy of the individual branches. Now the summation of the entropy of the individual branches and the parent entropy, if we find the difference, okay, that gives us the information gain. That is the information gain. How much information uh, we have received or we got after splitting the data set according to that attribute and according to that decision. Okay, so now how to calculate the entropy, and what is the entropy measure? It is the negation of, um, as you can see, uh, first of all negation and then the summation of pi log to pi. Now where we have C is the total classes and pi is the probability of picking a data point with class I. Okay, so we will further discuss these things, and we will be able to understand it when we go through the numericals and the hands-on in one of our next videos only. But just to highlight some things, okay, let us say our that play, the badminton notion use case, if you take, so here the number of classes is going to be 2. Okay, and so it will be the probability of the game being played and multiplied by the log of the probability of game being played plus probability of game being not played multiplied by the log of probability of game not being played. So I don't know how much you understood by the way I just tried to articulate it in some text form, but we will definitely understand it when we go through the video on hands-on. Okay, so this is where the entropy is measured. Now, minimizing the entropy is equivalent to maximizing the information gain. That is what we have seen earlier. And the value of information gain, IG, lies within the range 0 to 1. 1 means maximum. Okay, so the value of information gain will always be between 0 and 1, and the entropy is maximum, then information gain is going to be towards 0. If entropy is low, then information gain will tend to reach towards 1. Now, there is some another thing. Information gain is calculated for a split by subtracting the weighted entropies of each branch from the original entropy. When training a decision tree using these metrics, the best split is chosen by maximizing information gain. So that is why I tried to explain you or articulate you in the previous slide also, that we will calculate the entropy for each of the nodes and the child nodes entropy summation, which is subtracted from the parent node entropy, and that is the information gain. And in this way we will keep on trying for various features, and the feature for which we get the maximum information gain, that feature we will use for splitting. So in this way, we will decide what feature is to be used as a root node. After root node, further which features have to be used for the further splitting of the decision tree. So now if you can see here, this is some automobile, second-hand automobile site, olx.com, like kind of that thing. So here it gives the age of the automobile, then the mileage of automobile, and whether it is tested on road, and whether it will be bought or someone will purchase it or not purchase. Okay, so these are the various values: age, recent, this thing, mileage, all these values. Some data set, some small data set has been shown, and they have given the information gain. Okay, for age, the information gain is 0.3112. What does this mean is, if we take age as the root node, as the feature for the root node, and depending on this age, whether the age is recent or old, we try to split the data, we get the information gain as 0.3112. If we take the mileage as the root node and try doing splitting, we get information gain as 0. And if we take road tested feature as the root node, then the information gain is 1. So just think and tell that which feature should be used for the root node. In this case, we have the information gain for each of these features. So as discussed, we will take the feature which is having the maximum information gain, that is the road tested. So in this data set, road tested will come as the parent node. Depending on it, the further split will be done. Okay, so the maximum information gain is for the feature road tested, and therefore we will select this to be our first split feature. So this is one of the scatter plots which we saw in the initial beginning itself. Initial first or second slide only we had seen this scatter plot. So an information gain of 1 is the highest and best possible impurity. It shows a perfect homogeneity. It can only be achieved when everything is the same class. Okay, so in this way we have tried splitting the data set. Okay, in in the left side you can see that we have created a model such that x is equal to 1.5 somewhere. Okay, this is the model that we have created, which is not giving us a perfect split. We can see that one of the blue balls is going in the classes of the green box. Okay, so in this case entropy is going to be more and the information gain is going to be less. While if you consider the next, the scatter plot on the right side, x is equal to 2 is our model, and which is giving us the perfect perfect results. And as you can see, the information gain should be 1 in this case, and it gives a perfect homogeneity. Now, apart from entropy and information gain, there is one more parameter which can be used to decide uh, the features which features to be considered for splitting, which is called the Genie Index. So we can either use Genie Index or the information gain. Both or anything can be used out of these to find the features that have to be used. So if you just look at the formula in entropy, the formula was little similar. The only thing was pi, the probability of picking up the ith class, was multiplied by the log of that probability. So if you just go back, see, this was the formula, okay, for entropy. And if you come here for Genie index, a little variation is there. So instead of log pi, we are using 1 minus pi. Okay, so in this way, Genie index will be calculated. Genie coefficient can theoretically range from 0, complete equality, to 1, complete inequality. So here you can see that we saw information gain is equal to 1. We want information gain as 1. Okay, but just opposite to that, Genie coefficient has to be 0 for complete equality. Okay, so it is sometimes expressed as a percentage ranging between 0 and 100. Gini coefficient should be 0 or near to 0. So just it is opposite to information gain. We want information gain as 1, while Gini coefficient we would like to have it as 0 or at least near to 0. Okay, so the same thing, the same plot here has been shown, and a Gini impurity of 0 is the lowest and best possible impurity. It can only be achieved when everything is the same class. Okay, so Gini index of the right, on the right, if you can see, the Gini index is going to be the lowest, that is 0, and the information gain is going to be the highest, that is 1. So what is a good Gini index number? Let us take a use case of income distribution in a country. So in a country, um, this income in a like a country like India, where you can say there will be a high range of income distribution. There are some people who are the Asia's richest people, while there are some people like below poverty line. Also, the maximum lot of people below poverty line are also existing in India. Okay, so here there is a lot of disorder existing. Okay, in the income, if we take the income distribution data set, then there is a lot of disorder existing. So Gini index would register a reading of 1, which indicates perfect inequality in income. Okay, if everyone had the same amount of money, the index would register a reading of 0. So because income distribution, it is having a perfect disorder in a country like India, so Gini index will tend towards 0, while the information gain will tend towards 1. Sorry, just opposite. Gini index will go towards 1 and the information gain will go towards 0, because there is a perfect disorder existing and we are not getting any kind of information gain out of that data set. Okay, the number can be multiplied by 100 in order to express it as a percentage. What is Gini gain? We will see it in the numerical example. And while deciding on which node to split, a maximum Gini gain is desired. So till now we saw that we were using decision tree for a classifier kind of thing, where the target was a categorical variable, but decision tree can be used for the regression kind of use cases also. So for such kind of use cases, you calculate the R2 of data sets before and after splitting. So if we want to recollect, just give me 1 minute. Okay, so if we want to recollect R2 from the linear regression chapters, R2 can be understood as the proportion of variation of dependent variables, which can be explained from the variance of independent variables. Okay, so coefficient of determination or goodness of it. So if R2, generally it is between 0 to 1, and the if it tends towards 1, then the coefficient of determination is good and our predictability or the our accuracy will be good. So if we want to use decision tree for regression, so we calculate the R2 of data sets. So earlier we saw we calculated the entropy and then summation and then subtraction. Now instead of entropy and all those things, here we will be calculating the R2 of data sets, and then calculate R2 in the similar manner to what you do for linear regression models. Split the data such that the R2 of the partitions obtained after splitting is greater than that of the original or parent data set. So this we have to consider now, that we will calculate the R2 of the child nodes as well as the R2 of the parent node. And if the R2 of the child nodes is better than the parent node, then that feature we have to consider for splitting. In other words, the fit of the model should be as good as possible after splitting. So it is, if you just think from physical significance point of view, then also you will understand that after splitting, there has to be a better correlation between the data set. That is what we want. And that is how we will select the features for splitting. Now, in decision tree regression, when to stop, when the R2 is acceptable or MSE is 0 or near to 0 or minimum. Okay, so here we just tried putting some runtime values or the real time values to the variables of X, MSE, and we tried observing. So in the root node, we are having some feature as X, okay, and the decision tree is if X is less than equal to 148, we are splitting on that decision, okay. After splitting, we got the MSE of 1.853. These are the various values that are received after splitting. Or initially in the root node, we are having the total samples of 5. After splitting, the total number of samples in left you can see as 3, and in the right you can see the total number of samples as 2. They have given the other values as MSC and the values of X also. Now further down we are splitting it. If X is less than 99.52, so if you can see the number of samples is also going down, the MSC values are also reaching towards 0 slowly. Okay. So in this way, we will keep on splitting until we get some R2 value which is acceptable or MSE which is 0. So they have depicted this diagram taking some of the real-time values of mean square error and some other values from the data set. So these are some of the links to the hands-on exercises which we'll go through in our just next video. So hope you were able to understand the theory of the decision tree and regarding the various measurements like entropy, information gain, Genie index and everything. We will further dig on these concepts when we are going through the hands-on. So thank you so much. I hope this session was uh, you were able to get some things out of this session. So bye for now.